Hello. Okay. Hi, everyone. Good evening. Welcome. I'm Pramod Satya from IBM. And today I'll be talking about the work we did last year on the Velox expression optimizer. Start with an outline of the talk. First, I'll go into the motivation behind the project, what led to a dedicated expression optimizer in Velox. Then I'll go into the internals of the expression optimizer. After that, we'll look at how the optimizer enables extensibility by design. Then we'll end with a case study involving the Presto sidecar. Okay, let's start with the motivation. So last year, the Presto team at IBM, we proposed a native SPI for Presto C++ in order to close certain critical functionality gaps that we noticed in C++ and to reduce correctness issues that were resulting from having a split brain between a Java-based coordinator and C++-based workers. So I won't go into much details about the native SPI. There's a detailed RFC in Presto, but essentially the goal is to extend Presto's plugin interface to be able to customize the Presto coordinator functionality in C++ clusters. And one such customization that we wanted was an expression optimization during query planning in Presto. So the Presto planner, it optimizes expressions in order to make query execution more efficient. And previously in C++ clusters, this plan time optimization relied on a Java-based expression optimizer, and this used Presto Java's expression evaluation. And as part of the native SPI effort, we wanted to ensure that the Presto planner optimizes expressions using Velox's expression evaluation. And this is really necessary because we want to ensure consistent expression evaluation semantics during both planning and runtime. So essentially what we wanted to add is a native expression optimizer in Presto that delegates expression optimization to the Velox's expression evaluator via a sidecar process. So the sidecar process, it's just a Presto C++ worker with a few additional capabilities. And one of this capability is expression optimization. So this native expression optimizer, it should have the same capabilities as Presto's default Java-based expression optimizer. And for this reason, we wanted to bring in all of Presto Java's expression optimizations into the native expression optimizer. So we started looking at how Presto Java optimizes expressions. And we noticed that in addition to constant folding, Presto is quite aggressive when it comes to expression optimization. It uses a bunch of logical rewrites. Let's take a look at one of the examples. So here we have a sample expression tree with a nesting level of 4. This is just used for illustration and doesn't represent an expression from any actual workload. So right off the bat, you can see that you have a 1 equals 2 here, then a 3 plus 4, and then 4 between 2 and 8. And these can all be folded. So that's what happens in the first pass. You fold these from the input. 1 equals 2 becomes false, and then 3 plus 4, 7, and the between evaluates to true here. And then again, you see that this if can be simplified as well. But here C0 and C1 are columns, so you cannot actually constant fold it. You need to infer that because the condition is false, this subtree can simplify to C1, which is what Presto does. And it simplifies this subtree to C1. This is folded to true, and then this is an invalid cast. So what Presto does is it replaces this with a fail expression. So in the second pass, this is the transformation that happens. And you now end up with a coalesce with 3 inputs, C1, null, and C1. You can get rid of null here, and C1 is a duplicate input to this in the subtree. So you can deduplicate it, and you can essentially simplify this whole thing to C1, and you can get rid of this true input to AND here. So essentially, you end up with a much more simplified expression tree with Presto. So in this example, we took a look at the coalesce and if logical rewrites that Presto does, but it has a bunch more logical rewrites that in conjunction with constant folding really optimizes your expression. So let's take a look at the conjunct expression. So let's say you have inputs that have been folded to true. Presto just prunes those inputs. And if you have any input that folds to false, it just short circuits evaluation and returns false instead. Similarly, for a disjunct, it prunes false inputs and then short circuits evaluation to true if possible. And for a curless expression, it deduplicates inputs, prunes nulls, and simplifies if there's a single expression remaining, as we saw in the example. And then for a switch expression, let's say you have a condition that is folded to false, so you don't have to evaluate that condition. You can just prune it from your switch expression, and that's what Presto does. And you can short circuit if the first condition that you see can be folded to true. If we saw that in an example, and for the in function, let's say the value that you're searching for in your in list is constant, but your in list has certain like variables or column references in it. So constant folding will not be able to evaluate it, but if your in list has the constant that you're looking for inside it, you can still simplify that to true and short circuit evaluation entirely. And Presto does all of these. And what we wanted to do is bring in all these optimizations from Presto Java into Presto C++ or Velox in order to enable Velox-based expression optimization during planning in Presto. So before looking at how we brought in these optimizations by adding an expression optimizer, let's first take a look at how expression evaluation happens in Velox. So Velox provides a user-facing typed expression interface, which is the logical representation of your expression. And in Presto C++, when you convert your Presto plan fragment to an equivalent Velox plan, or the Presto row expressions are converted to Velox typed expressions as part of this plan conversion. So you end up with a Velox plan that has these typed expressions. And in order to evaluate this, Velox first compiles it into an executable expression using an expression compiler. And this is where optimizations used to happen in Velox before, such as constant folding. Let's zoom into the expression compiler a bit more and see what actually used to happen in there before. So the expression compiler, it would optimize the shapes of certain scalar functions to enable better execution. And it had a rewrite framework that was internal to the vector function module in Velox, and it wasn't really extensible outside of it. And the compiler would also constant fold expressions, but the API that it used, it would consume an executable expression and produce back a folded executable expression. So what this meant was constant folding was not extensible as well outside of the expression compiler because it was tied to an executable expression and not the user-facing Velox expression API. So to sum up, because these expression optimizations, they were entangled within the expression compiler, it was not really extensible, and this made reuse harder for components that just wanted the expression optimization semantics without actually having to evaluate the expression with Velox's expression evaluation. And we ran into this issue when working on the Presto native expression optimizer. So now we move to the new design with the expression optimizer. So the expression evaluation pipeline still looks pretty much the same. It starts with a typed expression from your Velox plan and ends at execution. But optimization is now a standalone module over typed expressions. So instead of being abstracted within expression compilation, it is now explicit and reusable with this new module. So what this does is it keeps your execution path intact, and it removes the unnecessary coupling that used to exist between optimization and compilation. So in this slide, we can see the key API contract. Optimize is the key API here, which takes in a typed expression, returns an optimized typed expression. And the expression optimizer essentially produces an artifact that you can port, and different consumers can use it. For instance, it could be used by Velox's expression evaluation, as it is today, or the Presto sidecar with the native expression optimizer, or future backends like QDF. Two parameters are kind of important here. One is the query context, which allows users to pass in query level configs like session time zone, etc. And the make fail expression parameter, it's essentially a function which allows developers to inject engine-specific failure handling semantics into the expression optimizer. So let's say a subtree fails during constant folding. You want to be able to specify how to handle that failure, and you can do that with the expression optimizer. Let's take a deeper look. Here's the behavior model for optimize. It's going to run bottom up on your expression tree. So children are optimized first. Only if all the inputs to your subtree are constant, it tries to constant fold or evaluate the subtree. If not, it is going to attempt to rewrite the subtree into an optimal form. So one thing to note here is we don't evaluate non-deterministic functions in an expression, and this is to preserve deterministic consistency. What happens if constant folding fails for any subtree with a user level error? Say your expression contains a trivial error like divide by 0. So the optimizer, it allows you to catch such errors and inject custom error handling policy through the make-fail expression parameter that we looked at before. So essentially, this gives you a practical mechanism to preserve the expression type and semantics in the face of failures. And all of this happens without blocking optimization of the rest of your expression tree. So summing up, optimize is a deterministic API. It starts with a post-order traversal of the tree, folds eligible subtrees, rewrites otherwise. And these invariants, they allow developers to focus on the actual expression rewrite or the expression transformation logic without having to worry about the internals of how the optimizer is going to handle it. So the rewrite mechanism, let's take a closer look at it. So in this slide, we can see the core API surface for expression rewrites. And in order to enable these rewrites in a clean manner, we decided to add an expression rewrite registry in Velox, which provides a clean API contract. So first you have a register rewrite API. Using this, users can register custom expression rewrites, which are essentially expression transformations at the typed expression level. And the set of Presto expression optimizations that we looked at before, they're not really specific to Presto, and they're engine invariant. So the Velox expression evaluation, it actually registers these rewrites into the expression optimizer by default. And these are the rewrites for conjuncts, disjuncts, coalesce, switch, and if expressions. After that, you have the rewrite API, which is essentially going to iterate over all of the rewrites that you have registered, and then it tries to apply them in the order in which they were registered. So rewrite, it's either going to return a transformed expression or a null pointer if the conditions of the rewrite were not met. And once a matching rewrite is found, you just stop there and return the rewritten expression. And clear allows you to clear all the rewrites from the registry. So with this framework, all of your expression rewrites, they're registered centrally, and they're applied during expression optimization. And as a developer, you can easily inject any expression rewrite that you want into the optimizer, and the framework is going to ensure that the rewrites are applied in an ordered fashion, so the result is always deterministic. Let's now go back to the same expression tree that we looked at before. There's a small change. You have a user-defined function, let's say foo, over a single variable, let's say a, which returns a Boolean. And you have a rewrite register that says that if your argument is a big int, then you rewrite this to bar. It's quite trivial, but let's run with this example. And the rest of the expression tree looks pretty much the same. And we'll walk through how the Velox expression optimizer folds it in stages. So 3 plus 4 here, this was going to be evaluated to 7, and this subtree is going to evaluate to true. And now when you come to the next layer, this subtree is going to be folded to true, and then the fail expression is going to apply here. Let's assume that via the make fail expression parameter, you have injected the Presto fail function. So essentially, when optimization fails for any subtree, you replace it with Presto's fail function. So what happens now is your cast expression, which is not valid, it's going to get rewritten to presto.default.fail. And then your foo function call is going to be rewritten to bar. And because we now add the and rewrite, which gets rid of your true inputs, you eventually end up with this expression tree, which is identical to what we used to get with Presto. Okay, in this slide, we summarize the extensibility of the expression optimizer. So first, we have an expression rewrite registry, and using this allows us to define expression-to-expression transformations easily in a pluggable manner, and you can register a rewrite at any layer, and it always happens deterministically. And second, you have a fail handler hook, so you'll be able to customize failure handling during expression optimization per your engine requirements. And the third is the optimized expression is a typed expression, which is what Velox exposes externally. So it's portable across different backends. So together with all these three features, we ensure that the expression optimizer, it can handle different use cases without increasing the core complexity of the optimizer. Okay, finally, let's go back to the case study with the Presto sidecar that we looked at in the motivation section. And take a look at how the Presto native expression optimizer, it's implemented in the Presto sidecar. So first, the coordinator is going to delegate expression optimization to Presto C++ during the planning stage, and it will send over a list of Presto row expressions serialized as JSON over HTTP along this V1 expressions endpoint that we added. And the core expression optimization, the logic resides within Velox's expression optimizer. Presto C++ sidecar, it just takes care of the expression conversion logic. First from your input Presto expression to a Velox expression, and then your optimized Velox expression back to a Presto expression. And in order to enable this Presto to Velox expression round trip, we added in a Velox to Presto expression converter. And the sidecar, it's able to preserve Presto's failure handling semantics by injecting the Presto fail function into the Velox expression optimizer. And any new rewrite that you add into Velox, it becomes available immediately to the Presto planner. So an overview of the expression optimizer, the before and after. Before, optimization was buried inside the expression compiler. It was tied to a single backend, and now it's a reusable pass in its own separate component over typed expressions. And it has explicit hooks and boundaries to enable usability and extensibility. So in keeping with the core Velox design principles, this optimizer is reusable, extensible, and composable. So this was a large refactor in Velox core, and I would like to specially thank Christian Zendra from IBM for collaborating with me in making this a success. And also special thanks to Aditi and Masha for helping with code reviews. And thanks to everyone else who made this a successful community effort. Yeah, happy to take any questions.